Okay, so it's my pleasure to welcome Colton from Louisiana State University. He'll talk today about endoscopy for modular monodromic Hecke categories.
Well, thank you for having me. So I first want to preface with, it's the algebra seminar, but I don't really do too much algebra. So please interrupt me if you have questions. I'm content of getting as far into the slides as time allows, but if we need to stop earlier because of a lot of good questions, then that's perfectly fine with me. And so what I want to talk about is broadly some ideas that I've been having in terms of a sort of slow progression towards developing a theory of modular character sheaves that can actually compute some information about modular representations of finite reductive groups. So first, the boring, just some notation that will be used. So throughout, G is going to be a connective reductive group. I usually will have everything be over the complex numbers just to simplify a lot. And you'll have your usual suite of subgroups contained in that. So a Borel, unipotent, a torus, all that. And probably most importantly is that I'm going to be working with algebraically closed fields of positive characteristic, although I guess characteristic 0 is okay too. So some examples to keep in mind is QL bar, the complex numbers, and probably the most important one is FP bar. I'm also going to be working a lot with sheaves and sheaf functors, and I'm going to try to suppress a lot of this inner workings and technical mumbo jumbo. And we're just going to say that all the sheaves that we work with are derived, and the topology that will be used is the analytic one. So if you have questions about these as we go, feel free to ask, but we're trying to black box the sheaf theoretic stuff as much as possible. Okay. So with that being said, let me give a brief overview of a sort of modern perspective on what character sheaves are. This technically doesn't depend on the coefficients that we work with, but the basic idea is, the basic idea with character sheaves is you're trying to find a geometric theory of characters of finite reductive groups. So you can let a reductive group act on itself by some slightly enhanced version of conjugation that depends on the characteristic of your ground field. And by Lang's theorem, if you look at sheaves on this quotient stack, this is going to be just the same as the representations of the finite reductive group. So this is kind of a naive, this is some version of saying, well, those are the representations described geometrically. Now, this doesn't tell you anything about those representations. It's just some purely formal fact that comes from an equivalence of stacks, but you can take it for what it is. So we're not going to really be working too much with that, but we're going to simplify things a little bit. And instead of working with G being defined over FL bar, as I said before, G is just going to be over the complex numbers. So things should be really, really nice and simple. And a claim that I'll make without any justification really is that all the interesting behavior of representations of finite reductive groups is carried by this derived category of constructible sheaves that are ad G equivariant on G. Yeah. So
are you assuming that one are not the same?
Yeah, let's L and P are not the same. The only place that I'll ever use L that matters is this Lang's theorem part, which they're not the same is important. For the most part, I don't want to work over FL bar for the ground field. I want to work over C, but this is just some motivation. So from here, we can define the unipotent character sheaves by some push-pull along the so-called horocycle correspondence. So it takes sheaves that are B equivariant on G, but with respect to the right and left actions, and produces something that's ad G equivariant on G. And these are the unipotent character sheaves. They correspond to the unipotent representations of G, the ones that come from Deligne-Lusztig induction of the trivial representation. Now, this doesn't give you all the characters of a finite reductive group. In order to get all of them, you have to make well, you have to make the stack G mod B bigger. And so instead of doing G mod B, we could do G mod U, and then quotient out by the adjoint action of D. So this is almost, I mean, it's a torus away from being the top part. And we can then define the character sheaves as just the, in the same way by doing a push-pull correspondence here. So this is all fine and good, and you can produce some categories of things that look, I mean, that are sheaves and that contain some representation theoretic information in theory, but there's, I mean, this is all complicated and hard to compute anything with. And if someone asked you, oh, we'll write down all the unipotent character sheaves, with everything I've said so far, you would be helpless. You need some extra input. And classically, yeah, I guess, let me go to the next slide, but classically, this input has come from the so-called generalized Springer theory. So in the 80s and 70s, and to some degree before, there was a lot of work in terms of describing what morally is the same as these unipotent character sheaves using tools from Springer theory that allow you to compute what the stocks of these things are. They allow you to classify them. They allow you to really get an understanding of them. And the main second part of this story is then you can go and do a sort of Jordan decomposition, which lets you take general character sheaves and sort of makes you, lets you transform them into unipotent character sheaves. So the two-step process, if you want to really study character sheaves, is first you want to maybe understand all of unipotent character sheaves, and the second is you want to figure out a way to decompose general character sheaves to the unipotent ones. Now, I'm not going to attempt to really answer the first part. I certainly want to eventually, but it is quite difficult. There is a modular version of the generalized Springer correspondence due to Achar, Henderson, Giotto, and Risch. And in theory, this might allow you to study unipotent character sheaves, but it's the current formulation is not very computable. I mean, in the characteristic zero story, there's some nice algorithms that let you compute these stocks. I mean, it's still not easy, but it's certainly possible. Whereas at least right now, there's not nice methods in the modular case. However, so yeah, we're just going to kind of ignore that for now and really just focus on the second part. And what I want to do I mean, yeah, the goal today will be to go and really present a version of this Jordan decomposition that's done so in a sort of clever way. And I'll say that a version of this already exists in literature. Arnaud Tev, and like last year, put out a version of this for positive characteristic that is quite nice. It incorporates Frobenius. It's and is able to answer some nice questions. But one of the hard things that is produced is that these Jordan blocks that are produced in Tev's formulation are about as hard to study as the unipotent character sheaves themselves. I mean, a sense that we'll see shortly. So what I really want to do is to develop a Jordan decomposition for character sheaves, but to have some really tight control over the actual Jordan blocks, so that we can actually eventually study these unipotent character sheaves. And the main method of having these combinatorially controlled Jordan blocks will come from doing a sort of mixed lift of this problem, which we'll get to in here in a little bit. So this is kind of just all motivation. So before I proceed, is there any glaring questions or confusions? Okay. So let me give a sort of overview of constructible sheaves and particularly equivariant constructible sheaves. So when you study equivariant sheaves, there's usually, I mean, you first have to make sense of what it means to be equivariant. And the most natural thing is that you have some action of an algebraic group on a space. And what you want is that when you pull back along that action, you just get a constant sheaf as like a sort of eigenvalue. So you're really not too far off, and you look like a constant sheaf box tensor with F. And this is not enough. You need to, well, at the very least, you need to satisfy some sort of co-cycle condition. You need to be compatible with doing this multiple times. This can't just be any isomorphism you want. And really, since we're working with derived things, there's even more data you need to specify, but this is perfectly okay for now. And what I care about for the purposes of this talk is not usual equivariance, but it's so-called twisted equivariance. And what we want to do is we want to twist by a multiplicative local system on the group that we're working with. So if we have an algebraic group H, we can look at a local system that is rank 1, so it has one-dimensional fibers, and we can ask that when we pull back along the multiplication map, we just get 2 copies of the local system. So this is, I mean, this should be, yeah, I mean, and one interpretation is if we work with like locals, we work with representations of fundamental groups instead of local systems directly, then this is corresponding to some algebra structure on the representation. So we can give morally the same definition, just replacing the constant sheaf now with that local system. And this provides a new type of equivariance. The sort of multiplicative structure ensures that this co-cycle condition holds. And we have a new form of equivariance on these spaces that can give us some control. Well, yeah, we'll see how they're used in a bit. So here's, well, we'll do lots of examples because examples are great. So first, some examples of these equivariant sheaves. Well, the most basic example of an equivariant sheaf is just the constant sheaf on an algebraic group. Also, any of these multiplicative local systems are also equivariant with respect to themselves by the condition. So an easy example that we can come up with is if we take H to just be GM or C star if you prefer that. Well, local systems on GM are just going to be representations of the integers. And we can take the representation of the integers that maps 1 to minus 1, or in this case, I have t plus and minus, and it maps t to minus 1. And this defines a character of the group algebra there and defines a multiplicative local system. So using this general philosophy that local systems on a space are equivalent with representations of their fundamental groups, we can associate a multiplicative local system. And this itself is equivariant with respect to itself. And just some notation that we'll use throughout for usual equivariance. There's writing things in a stacky way. If this is weird, you can always imagine the H being down here and covering that up, but that's fine. Whereas for this, we'll always have like a little L next to the stacky bar, the quotient, to indicate that there's some, it's not a usual equivariance. So why, what sort of weird things happen when you start imposing this new equivariance constraint, these twisted equivariants? Well, here's a basic example. So GM acts on just the affine line by the usual scaling action. And what one can easily convince themselves of is that there's no GML equivariant sheaf on on 0, the point 0, unless the local system we started with is the constant sheaf. And the reason for this is that this small in 0 is too small to support such an equivariant constraint. All the sheaves on the point are just copies of the constant sheaf, direct sum together and whatnot. There's no equivariance that's not just the usual trivial equivariance. And so the key takeaway from this is that equivariant sheaves on the affine line, in this case, behave very similarly to just like if you remove the point entirely. So in particular, actually the category of equivariant sheaves here is just category of like vector spaces. And one consequence of this is that the IC extension of the local system that we started with here is not really anything fancy. It's just like a star extension or a streak extension. And so in particular, like this local system is, one description is that it's clean. And so I want to internalize this as this IC extension behaves like a skyscraper sheet. It doesn't have any interesting cohomology at 0. All the cohomology at 0 will be picked up by the equivariance It has no equivariance at 0. And so you just get something that's quite simple. Okay. Okay, so what I want to do now is explain how you then take these equivariant sheaves with respect to some local system and upgrade this to some theory of parity sheaves. So I'll say maybe a bit about parity sheaves. Parity sheaves have appeared as a sort of positive characteristic version of semi-simple complexes, and they are like really combinatorially controlled. They have nice cohomology. They're easy to work with, and more or less everything on the left is just existing work of many people, and the right is sort of this new setup that doesn't really require any more work, but just requires some routine nonsense. And I think in general, there'll be a lot of this throughout, where we have on the left-hand side will be usual equivariance, unipotent monodromy, that type of thing. And then on the right, we have some sort of twisted version, some monodromic version. And so the first thing I want to say about these parity sheaves is, well, one, I want to make sense of what it means to be a local system for one of these equivariant sheaves. So what does it mean what does it mean to be a local system? Well, the most easy thing you can ask is that if you started with a local system and you forget the equivariance, are you a local system? And the answer is yes, and you can go back the other way too. So if we have an equivariant sheaf and we forgot it and we get a local system, that's all it is to be a local system. And this is really the same in both worlds. We can always just forget, and if it's a local system, it's a local system. I mean, I'm saying that in kind of a tautological way, but like you have to make sense of what it means to be a local system on a stack, for instance. Anyway, from there, there's sort of like these parity conditions that one imposes on a space, and you need these parity conditions to hold in order to have a nice theory of parity sheaves. And so the usual way that this goes is that you ask that the cohomology of your spaces is concentrated in even dimensions, and that there's no odd dimensional extensions of local systems. So that's what those first two conditions on the left are saying. Now, one minor thing that happens in this equivariant or this twisted equivariant world is that there's no longer a notion of cohomology, and at least not one that produces something on a point. I mean, that's how you should think of these cohomology of sheaves, is it produces some complex on a point. But we already saw that most of the time, whenever you take a local system that's not the constant sheaf, you're not producing cohomology on a point. That vanishes. So instead, we just use this second characterization, and it in fact implies the first characterization using a classical theorem that relates the equivariant cohomology with homomorphisms from the constant sheaf. Nonetheless, we can define these, and it's more or less the same. We just don't want we don't want any odd degree extensions or odd degree homomorphisms. And whenever we do have such a setup, we have something that satisfies the parity conditions. We can ask whether a sheaf is even or odd, and it's very much it rhymes. So you ask, or a sheaf is even if itself and its Verdier dual has no odd degree homs from any local system on one of the stratas. So this is some condition that you check locally, where you look at a sheaf, you restrict it to each of the stratas, and you see if there's any odd degree homomorphisms. And then what it means to be parity is it admits decomposition into something even and something even, but we shift by one. So if something is even and we shift by one, it'll now be odd because we've shifted everything by one. So it'll have things in odd degrees, but that's okay as long as there's a nice direct sum decomposition. And so there's a general philosophy that was mostly given by, that was done in probably about 2016-ish, which was that a lot of times you have these semi-simple complexes that appear in characteristic zero representation theory. And what you want to do in positive characteristic is replace these with the so-called parity sheaves.
Can you
any condition work out on most two method criteria? Like how much stronger is it than all this better even dimension?
So yeah, I think this is like one, this is a great question. And in the case that your stratification is like simply connected, so there's no non-trivial local systems, all the parity conditions are stating is that the cohomology is concentrated in even degrees. So it reduces just to checking the cohomology strata. In general, like you might have non-trivial local systems, you have to compute the cohomology with respect to that local system, which isn't much more, but is, yeah.
Does it depend on the characteristic?
Yeah, I mean, so you can be in a case where the cohomology in like you can imagine your cohomology has some prime torsion, and so if you were in characteristic 0, for instance, that prime torsion gets killed, but in characteristic P, you see that and you pick it up, and that makes something in odd degree. Can I answer your question? Yeah.
Sorry, I see, I sort of built into the line, sorry, the middle line of the definition. So I don't see an iron.
Oh, sorry. There should be a shift by I here. Yeah, apologies.
Okay. That would make sense.
Yeah, it should very much rhyme like with the parity conditions. Okay, so this is a lot of like sheaf theoretic nonsense, and I think that'll be like the bulk of the sheaf theory nonsense that we need. So let's now see some Hecke categories. So the Hecke categories on the left is very classical. So it's constructible sheaves that are B equivariant on the flag variety. And this is pretty well understood in both characteristic 0 and characteristic P in some ways. There's not too much to say, but well, yeah, I mean, these have like a rich history. They appear in a lot of this work of Kazhdan and Lusztig in the 80s that's now called Kazhdan-Lusztig theory. And it should be thought of as some like categorification of the Hecke algebra. So there's some sense that if you take some notion of growth and group, you produce the Hecke algebra. And also these things like should be thought of as, I mean, there's some general sheaf function correspondence that tells you like sheaves should map with functions. And so, yeah, I mean, that's, I think, where a lot of this comes from. And the Hecke algebra actually admits an act, like it itself is a representation of G, or more so it's the Hom space of two representations. And it really, like this usual Hecke category captures all the interesting behavior of unipotent character sheets. And I'll say more of that in just a minute. But yes, some basic facts with them is that one, there's some convolution. It has a monoidal structure. It's not the usual tensor product of sheaf structure. It really should be thought of as something more analogous to convolution of functions. And there's a bunch of objects that one usually cares about in characteristic 0. These are these so-called IC objects, these simple perverse sheaves. In the positive characteristic world, there's these parity extensions, which are these replacements for the ICs, and are defined in a somewhat complicated way. And so this is all on the unipotent side. On the monodromic side, we want to cook up another type of Hecke category, but that's able to incorporate not just the unipotent things, but the ones with arbitrary monodromy. And the solution to that is using this twisted equivariance. So instead of taking G mod B, we can take G mod U, and then we quotient on the left by a torus with some monodromy, some local system, and on the right with some other local system. And these can be different. They don't have to be the same. And then we can just take the sum of all of these categories. So this, I say sum as in like, not, yeah. You just imagine they're all assembled into one big category. And this is perfectly fine. It also has a convolution. It doesn't quite send, it's not quite what, each one is not quite monoidal unless the parameters are the same. So in if you have L and L on both sides instead of like L and L prime, it is monoidal. But in general, the whole thing is monoidal. It'll take L, L prime, L prime, L double prime to L, L double prime. So it kind of matches up in the middle, and you lose that part. And just like in the usual case, there's some sort of classical set of objects that one would care about. There's these IC objects that are defined in fairly similar ways. And what I want to do is just write the monodromy parameter, and this is the right equivariance. So whenever I write like ICWL, that means it has on the right, it has L as the equivariance to the state. And so we also have parity extensions, and proving that these exist and all that is very similar to the usual case. There's not too much interesting that goes on. But one interesting thing that goes on is that a lot of things get killed. So just as we saw before with the GM action on affine line, not every, like this equivariance constraint makes a lot of things go to zero, makes things not able to be supported. And so in this case, if you want to ask what the equivariant sheaves are on the monodromic Hecke category with monodromy L on the left and monodromy L prime on the right, it's just going to be the things, well, there's some W action on all these local systems that's just given by pulling back along the W action on the vowel group action on a torus. And what we're imposing is that what we want to look at is a subset of elements who, when we pull back along the monodromy parameter, we get the other one. And so the only things that are going to be supported in this monodromic Hecke category are going to be the ones that take L to L prime under the vowel action. So it's a lot smaller. I mean, the main thing you should interpret this as is if we fix the monodromy on both sides so it's an equivariance, then the possible objects that we allow is going to be a lot smaller than what we started, smaller than W. With one special case, which is if we take L and L prime to both be the constant sheaf, then we recover everything that is on the unipotent side. So there, everything is fixed by the vowel group. The vowel group, whenever you pull back the constant sheaf, you always get a constant sheaf. And so everything there is that small. And so these are, I mean, both sides of this story have been covered in some amount of literature already, with the left side being much more and the right side maybe a little less. But there's a lot of progress and a lot of descriptions of how these things relate to character sheaves. So in going back as early as 2009, Bensby and Nadler proved in characteristic, when the characteristic is 0, that the categorical trace of the Hecke, this left side Hecke category gives you unipotent character sheaves. And there's also a lot of other, I mean, yeah. And then in 2016, Zhu proved this for positive characteristic. And then in 2016, Lusztig proved a version of this for all character sheaves in the monodromic Hecke category when characteristic is 0. And then recently, Atev proved for a positive characteristic that the monodromic Hecke category, when you take the trace, you get all character sheaves. So this is a lot of names, a lot of like slight variations of the same idea. But the key takeaway from all this is that the Hecke category encodes all the information that one might want to know about character sheaves. So there's some reason for wanting to study these is that you can reduce studying character sheaves to just studying these Hecke categories. And there's a lot of nice things about these things. One, we know, there's a nice orbit stratification given by these Schubert varieties. They are all close. I mean, they're not quite affine, but pretty close. They have easy descriptions of the simples and so on. Whereas, like, for instance, sheaves on G, like G equivariant sheaves on G, and with respect to the conjugation action, it's much more complicated. There's infinitely many orbits and it's a lot that we don't know. Okay, so the rough goal is to spend more time on the monodromic side and try to and find some information that can maybe tell us some more about the character sheaves. Okay. So the next really concrete, I mean, this next part is really concrete and hopefully should be a little bit of a little refreshing compared to the abstract sheaves and whatnot that we had before. But the main idea, yeah, so associated to any of these multiplicative local systems, I want to construct some smaller group than G, and this is called the endoscopic group. The basic idea of this is that we can look at a subset of all the co-roots who, when we pull back along a fixed co-root of the local system, we get the constant sheaf. So this gives you some subset, and it in fact defines some subroot system of the ambient co-root lattice, and we can then just create some group from it, which we call the endoscopic group. So it'll have the same torus as the group we started with, and it'll have some collection of the roots, but it's not a subgroup. I want to emphasize, not necessarily a subgroup, not necessarily like a parabolic, not necessarily a parabolic subgroup. It's kind of just its own thing. And probably the most interesting aspect of this is not maybe the algebraic group as itself, but it's file group. And so we can we'll denote this with WL-circ, and WL-circ is going to be a subgroup of the ambient file group, but it's kind of a weird one, and it's not going to be like a parabolic subgroup. It's not going to be a subcoxeter group in the sense that there's a length function on WL-circ from just simple reflections in the file group, but those simple reflections need not be simple in all of W. So they could be.
Well, in general, you can get all the subroot systems by using all the signal.
Sorry, you can get all the.
Subroot is by using the Baron signal.
Sure, there is classifications of endoscopic groups.
Yeah.
Yeah.
That gives you exactly.
Yes. Yes. You can. I mean, this definition is more sheaf theoretic than like what you need. You can associate it to one of these local systems. You can associate a element of the Langland's dual torus,
yeah.
And then you can use this general like machinery that it's more classical and like Langland's in terms of producing these. But yeah, I mean one thing that is I'm not sure if is it for Kakmuti groups. I don't think there's this similar classification, whereas you can still make this definition and.
Because I mean, the way you do it is you just extend and think about it. And then you can actually pick off these subword systems using extended thinking.
Yeah, but yeah, I mean, these are very computable. You can like explicitly write down the local systems. You can explicitly write down how they act on the roots and like, yeah, I mean, there's yeah, you can write computer code that computes these in like really crazy cases, and it's not too bad. Anyway, so here's a very motivating example, which is we take G to be SP4, G check will be SO5. We can define a character on the torus here where we assign a character on the fundamental group of the torus, which takes both the generators to -1. So this has degree 2. If we multiply it with itself, we just get 1. And this gives us a multiplicative local system that is not the usual one. And what happens is on the co-root side, it'll pick out just these 4 roots. And when we dualize them, we get these ones. And so we can see it from the diagram that this is going to be of type like A1 cross A1. So it's very simple. It's going to be generated by the file group for it is generated by the reflection across the root beta and then this alpha plus beta. And what I want to specify or emphasize is this subgroup is not a parabolic subgroup, right? This is a simple reflection in W. This is not like the length of this in W is 1. The length in this in W is 3. So these are kind of peculiar groups. Nonetheless, they're like, yeah, you can still really work with them. Okay. So what I want to do now is move a little bit back to some complicated nonsense, but hopefully keep things more manageable. So ultimately, I want to care about these Hecke categories that I defined before, but for fairly, I mean, yeah, in general, they're kind of hard to study. And the biggest reason why they can be hard to study, I mean, even in characteristic 0, is that there's not necessarily an easy subcategory that really controls the whole thing. Now, yeah, I mean, one of the reasons that people have studied perverse sheaves so fervently is that oftentimes perverse sheaves tell you something about the ambient derived category. And what happens in, like, if you work over which like normal varieties or something without any equivariance, is that you can, like, perverse sheaves tell you everything, and that you can always take the derived category of those perverse sheaves and you get the whole derived category. In the equivariance world, and particularly when you take with like these twisted equivariants, this doesn't hold true. So even though we can make sense of perverse sheaves, they don't tell you the full story. So we don't want to, so kind of a swing and a miss. Perverse sheaves is maybe not quite what we want to do if we want to study the full category in some clean, tightly controlled way. Another option, which is maybe slightly weirder, is instead of using a T structure like perverse sheaves, you could use a co-T structure. Now, most of the time, these do not actually admit a co-T structure, but they almost do. And the almost part is these so-called semi-simple and parity complexes. So these form some additive category. They're not abelian categories, but you can talk about like some version of like a T structure definition, which is in some sense dual. And one nice thing about co-T structures is that they always encode all the information of the category if they exist. So what I want to do then is sort of do this artificial, purely homological definition where I will a version of the derived category into existence that just uses semi-simple or parity complexes. We don't really have to, yeah, I mean, there's a fairly large story with this where it comes from, and in the characteristic 0 case, this usually does produce the usual mixed sheaves that comes from, say, like a tall geometry. But in positive characteristic is like purely formal, just some convenient thing we can do. And it's a lot of work then to take this purely formal thing and produce something that actually tells us something about the original category, but we'll get there when we get there. So here's an example. We're going to ignore twisted equivariance just to keep things really simple. If GM acts just on a point, so we're looking at equivariant homology of a point, well, the parity sheaves on this just correspond to 3 graded modules over the polynomial ring. And then when we, I mean, this is some little algebra thing, which is if these 3 modules generate the full derived category by the bounded homotopy category. And so what we get is all the differentially graded modules over this polynomial algebra, where now X has degree 2 common 2. So this is, yeah, I guess if you remove the M, then some like very, yeah, I mean, if you remove the M, then all this is saying is sheaves on a point mod GM is the derived category of modules over the cochains of the classifying space. So in this case, the classifying space is like CP infinity. And so it has cohomology in degree 2. It's some polynomial ring. And now we can add an extra grading from that's picked up from the fact that there's a shift for parity sheaves that's given by the shift in the ambient derived category. So it's some graded version of this like classical story.
So this related to like a correspondence at all? Example.
What do you mean?
Well, in terms of exterior arguments.
Yeah, and if we have time, we will talk more. But yeah, so if you look at sheaves on GM,
yeah,
then this is like very closely. I mean, if you look at the sheaves generated by the constant sheaf, this is the same as modules over the exterior algebra, and in this some sense, like these are causal dual to each other. There's yeah, well, I'll actually say more about this in just a little bit.
Similar.
Okay, yeah. Yeah, if we get a chance, we'll talk more. Like, I'll say for now, just in case we don't, mixed sheaves on GM in positive characteristic don't make sense. And when I, wrote down a while back, and the question Alberto asked was that, what's like a concrete description of like the parity conditions? Well, if things are simply connected, it's asking the cohomology is concentrated in even dimensions. Now, obviously on GM, the cohomology is not concentrated in even dimensions. So parity conditions fail there. And so the mixed category and positive characteristic is more complicated. But, well, yeah. Okay. So we can then do, like, we have some notion of mixed category that's dependent on parity sheaves, and we just define everything in the same way. So we just, and I'm not writing all the details here, but you take bounded homotopy category of the parity sheaves. They're still monoidal. They still have there's still like these sort of classes of objects that are retained in the same way. There's these parity extensions. Ones I didn't write before, which are these standards and co-standards. These standards and co-standards are even easier than parity extensions or easier than ICs. There's what we get by taking a local system and extending it to the full, a local system on a strata and extending it to the whole space. And there's two ways of doing this. You can do this either via like Schrick extension or star extension. In the Schrick case, we get standards. In the star case, we get co-standards. And since this is an algebra seminar, you should think standards are like Vermas and co-standards are like co-Vermas.
Is there a category, obviously category?
No, this is so like, like the perverse sheaves on G mod B mod U are highest weight, and that's category O. If you look at G mod B mod B, it's not highest weight, and no, it's just complicated. I mean, that's, yeah. A lot of this kind of comes back to the fact that perverse sheaves don't tell you everything about the derived category. So for instance, there's no tilting on these things. You can make a similar definition of like both these. I mean, in the monodromic case, where instead of having equivariance on one side, you ask for topological monodromy, and then those are highest weight, and you can talk about tilting and all of that. Yeah, and there should be some like very concrete representation theoretic, like it should be related to like category O, but in different blocks, something like this. Okay, so I wrote this a little while back, but the symbols here, the parities, the objects fundamentally are indexed here by the stabilizer of this local system in the Bow group. Now, the stabilizer of this local system is actually a little too big, and we want to go and shrink it down to this endoscopic file group we saw before. So the endoscopic file group, this WL circ, sits inside of the stabilizer, but it's not the full thing all the time. If the group has connected center. So all I want to do is take this Hecke category and just look at all the objects that have they're indexed by W being in this endoscopic file group rather than the full file group or just even the stabilizer. And this gives us some nice subcategory. It's in fact monoidal, and really that's where I want to imagine things to live. And so now we can talk about some actual results. It's been a big buildup, but so in 2020, Lusztig and Yun gave a description of these for characteristic 0, and what they were able to show was that if you look at the piece of the monodromic Hecke category that's L monodromy on each side, then this is actually just a normal Hecke category for the endoscopic. So the key, there's a saying in the theory of character sheaves, which is that non-unipotent character sheaves behave like unipotent character sheaves for a smaller group. And so this is one way to interpret this. This is some equivalence of Hecke categories, that this is the ones that are non-unipotent, and then they correspond to something unipotent on a smaller group. And so my contribution to this then is some positive characteristic version where we instead of having fundamentally this is like a fact about parity sheaves where we write the same thing, but now the coefficients are positive. But fundamentally, these are different things. Like this is parity sheaves. This is like semi-simple complex. So here's some remarks. This equivalence actually takes parity sheaves to parity sheaves. So this is like you don't even have to do this mixed derived category stuff. You can do everything with just parity sheaves. And there's also, Lusztig and Yun did this for reductive groups. The methods that we used actually works for arbitrary proximity groups, which had already been proved for a characteristic zero in some degree in Lee's thesis. But yeah, it's very general. Also, at the very beginning, I said that K was an algebraically closed field, and there's very good reason for doing this. But we can really make this flexible and make the ring be almost anything we want. I mean, the version of the Hecke category has to change, but yeah. And the last part is, we're looking at an individual, like where L is fixed on both sides. There's a version of this where we sort of simultaneously do this process for all the monodromy parameters, even the parts that aren't monoidal themselves. And we can go and create some sort of equivalence that takes the entire monodromic category, not just the ones with L on both sides. And this requires a fair amount of work and uses a bunch of abstract nonsense like two categories and whatever. So we won't get. Okay. Any questions so far? Okay. So in the last few minutes, I want to explain. I did a bunch of things, and then now we have some categorical equivalence. How can we go and then hopefully say something about character sheet from this? How can we use this to actually extract some information? And so the first thing, the first problem is we made this decision to work with mixed sheaves a little while back. And this was a good decision because we were able to actually prove something. But now we need to be able to go to non-mixed. And this is where problems start happening. And so in characteristic zero, there's always this sort of functor that takes you from the mixed thing to the non-mixed thing. And it's sometimes called a degrading functor, which is a really funny name. Anyway, it doesn't always exist in positive characteristic. And the way to think about this is something like in positive characteristic, when you write down on the right-hand side, on the non-mixed side, you can give it some description in terms of like DG modules over some fairly large endomorphism algebra. And the way you construct this is just by taking like all the simples, you add them all together, and you look at its endomorphisms. It's some really big algebra. It's really complicated. And what the degrading functor in positive characteristic is really coming from is like whether that algebra is formal. And proving things is formal is like really hard unless you have some like special trick. So we're kind of stuck in that even though we have some result for the monodromic side, we don't have the mixed side, we don't have a way to remove that mixed condition. And I'll say even like in the unipotent case, like we're just working the usual mixed and the usual Hecke category of G mod B mod B. The existence of this functor is so conjectural. Like there's not a description of it. But having the description of it, having such a functor lets you compute things in the non-mixed setting. That you just can write out the HOMs, and then they become HOMs here in terms of chain complexes of parity sheaves. And then the parity sheaves, there's a lot of computational tools using intersection forms that let you actually compute the homomorphism. So I'll say like having such a functor is more or less equivalent to being able to do any computation you want in the monodromic Hecke category, in the non-mixed. So it's very nice to have. So unfortunately, it doesn't really quite exist, but we can kind of get around it. And the way that we're going to get around it is by taking the causal dual of this category rather than the category itself. Now, this still has a lot of information, and it'll still go and produce the things we want. And in fact, it'll produce all the representation theory stuff we want. But it requires a fairly large leap in complexity. So what I mean by that, well, what do I mean by, I use the word monodromic in kind of two ways. There's one, this notion of equivariant monodromy, which is what we saw before. There's also one of topological monodromy. And all topological monodromy means is we have equivariant monodromy, this twisted equivariance we defined before, and we can forget it. When we forget it, this is forgetting some homological structure, but we can do it. And what we should, I mean, in one case, like you can imagine like sheaves on GM that are equivariant with respect to GM, that's just a vector space, whereas sheaves on GM themselves is like modules over the exterior algebra. So we can look at the category that's generated by just forgetting all these equivariant stuffs. So here's an example, which is if we start with the torus and we look at the unipotent monodromy, monodromic sheaves, it's just DG modules over the cohomology ring of the torus. This is concentrated in odd degrees, so we don't have parity sheaves, but not all is lost. Well, yeah, we can say a little more, which is like, how does this equivalence go? Well, they'll send the constant sheaf to this, I mean, to the like the whole cohomology ring, like the regular representation. And I want to emphasize that this is not compact, right? Well, I think actually it is in this case. And it's finite dimensional, but anyway, what I will mostly care about is not actually the cohomology here, but the augmentation module. And if we look at the augmentation module, it's really nice. It's compact, it's finite dimensional. And if you try to figure out what the augmentation module goes over here, it corresponds to some infinite dimensional local system. So not usually a constructible sheaf in the classical sense, but you can do it. And here's the biggest like jump or leap in faith is that you can actually construct these categories, these topological monodromic ones from the equivariant monodromic ones using, well, a Lurie tensor product. So this requires you to depart to the world of infinity categories. There's versions of this without using infinity categories, but you can't write them in one line. And so what's happening here is I want to pretend that these are all like modules in like that you learn in Algebra 1. So we have some ring, namely the category of modules on R. We have some, which is the cohomology here. We have some representation of it, which is category of vector spaces. The R acts on the category of vector spaces by forgetting, and R also acts here by means of like some version of convolution. And so we can go and then take a tensor product like we would in Algebra 1 and smile and be happy and not really unpack what is actually happening. But we can do it. And this idea is quite nice because if we hide this part, well, everything here we can make sense of in this mixed version. All these things we can talk about in terms of like parity sheaves, right? These parts didn't really depend on any geometry, and this we can talk about parity sheaves. So we can overall we can formally make this happen, even if like parity sheaves don't make sense. So so we do exactly this. We can do the same thing for the mixed case. We can do the same thing with the Hecke categories that we did before, where we have equivariance on both sides, so we're going to go and do the tensor product on both sides. We now care about things being mixed, so we have to work with DGG instead of just DG, but that's all fine. In this case, like the extra grading is just like the diagonal. And this has a lot of the same properties. I mean, this is like a complicated category to study in principle, but it has a lot of the same properties. It's monoidal. It has a special subcategory of so-called code-free monodromic sheaves, which for there's some BGG type relationship between these and the equivariant ones we described before. And in a lot of cases, we can write out pretty explicitly what it is. So if we just say GM, then what this is going to produce is exactly the thing that Dan said before, which is sheaves on the exterior algebra, or modules on the exterior algebra. And so this is like causal dual to the first one, essentially. And here, the Y has like no cohomological degree and purely internal degree. So anyway, this is some nonsense. I put this remark at the end where if we look at this subcategory of these co-free monodromic ones, this is in the non-infinity category world, there's a version constructed by Atar, Makasumi, Rishi, and Williamson that, well, it takes about like 100 pages to write down instead of one line. So I thought I'd favor the one line one. Anyway, but ours is a lot more general to it. It applies in a lot more setups than just where you have like Elias Williams mathematics. Okay, so the next part of this is that we can sort of formally will an endoscopic equivalence into existence in this purely formally induced monodromic way. So Guittard in 2021 proved in the non-mixed case that you have some in positive characteristic, there's some endoscopic equivalence of this form. The sort of key objects that one cares about are these like free monodromic, co-free monodromic tilting sheaves. And we can do the same thing, but ours never has to actually mention co-free monodromic tilting. It follows purely from the bi-equivariant one. So it's a very, very formal, but it's able to, yeah, I mean, it comes for free, but it's nice to have for free. And the last thing I want to say, because I think I'm over time now, is that on this bi-monodromic side, we can actually do degrading. So we have some chain of things. We can do endoscopy, and then some version of causal duality, and then, endoscopy, causal duality, another version of causal duality, and then endoscopy again. And in the end, actually, I think there's a typo, I think, where that should not be an M on this last one. Anyway, so we can do our endoscopy, causal duality, some formal thing, and then the Guittard's endoscopy equivalence. And the key takeaway is that this actually does give you a graded model of the category you started with. And then this has all the character sheet data we started before. We take the categorical trace of this, we get all the character sheets. So the hope is that if we study these mixed ones are controlled purely by Peacock and Lusztig combinatorics for the endoscopic groups. And so the hope is that we can go and then really give some explicit computations here by just understanding this Peacock and Lusztig combinatorics in the unipotent. Anyway, thank you.
So I should back up a little. So I'm thinking of this classical picture involving what's called the divergent triangle. So this involves the finite general linear, the Hecke algebra, and also the Q-sure algebra.
Okay.
Okay. And this is pretty well documented. And so you can also think about this more generally involving the finite equilibrium, the Hecke algebra, and also categorical irrational triangle. So we have these three options. Really, there are two of them up there. So can you do anything involving the rational triangle? Everything.
Yeah, I mean, there's certainly geometric categorifications of the rational triadic algebra. I haven't thought about how it fits in. I also don't know.
It's a quasi-rated cover of it.
Yeah.
So you have this nice structure which actually goes down to the Hecke algebra. The problem is the rational triadic algebra, and that's a quasi-rated cover. So it's the highest weight category. Not as bad. Think of the regular sure algebra like a symmetric.
Yeah, I mean, there very well could be a way of fitting this in. I don't know what necessarily the use of it is.
Well, The classic case, the transfer of information between, all the categories.
Okay. This is done in the like unipotent,
Yeah, the way it work is like different things.
Okay.
Like maybe this call.
yeah, I mean,
I'll send you that.
yeah, I mean, it'd be very interesting. I mean, at the very least, I think a lot of times it's fun to find like a way to geometrically define a functor, for instance. And so like, yeah, well, the endoscopic equivalence is not geometrically defined, but a lot of these things have, certainly geometric flavor to them. So
Thank the speaker.
thank you. There's also a diagrammatic description of all.
Oh, yeah.
So when you